Hi everyone, welcome to our webinar, Avionics Electronic EMC webinar. Thank you for joining us. This webinar is being hosted and presented by MET Laboratories. MET is a leader in the testing of electrical equipment for environmental hardiness, product safety, and electromagnetic compatibility. MET operates world-class labs in Baltimore, Maryland, Santa Clara, and Union City, California, Austin, Texas, and also runs operations in China, Taiwan, and Korea. This webinar will run 30 to 45 minutes with an additional 15 minutes for questions and answers. Due to the number of registrants, all attendees will have their phones muted. If you have a question, please type it in the questions area of your GoToWebinar control panel. We will attempt to answer all questions at the end. Just a quick note on some upcoming events. Military EMC changes MIL-STD 461G. It's been published, and there are a couple major changes from version F that will be held on July 19th, 2016, and we'll try to get some more information on that out to you. Today's webinar is being hosted and presented by Assad Bajwa. Assad is the Director of EMC Testing. At this point, I will hand over the presentation to Assad.
Thank you, Ryan. Folks, thanks for joining us today, and I want to apologize. Some of the technical difficulties we had yesterday were due to some technical issues. We could not correctly broadcast our webinar, so my apologies there. Today, as you know, the topic is to go over DO-160, which covers the environmental and EMC aspect of the testing compliance needs for commercial avionics. So let's go through this presentation. During the presentation, we'll talk about the role of the RTCA committee, what role it plays, how often they update the standard. We'll talk about some of the changes to DO-160 with Rev G, which happened over the years. Especially, we'll talk about changes from F to G when we look at some of the test methods. During the presentation, when we go talk about section 20, I will mention and elaborate a little bit more about two different methods which are used in industry for radiated susceptibility. Historically, as you know, people have been using absorbent line chamber, but now many standards, including DO-160, allows the use of reverberation chambers. So we'll talk about that, some of the challenges there, some of the benefits. We'll talk about those things. And towards the end, we'll focus on section 22, which is the lightning transient susceptibility test. We'll look at some of those waveforms, and we'll talk about some of the changes and how those testing is done and what might be the concerns when you guys are performing testing as a manufacturer of your products for avionics environment, and what needs to be done to make those products more hardened. So a brief introduction about the DO-160 so that everybody, especially the folks who are new to the DO-160, they understand the role of the standard is. So allow me to briefly talk about that, and we'll move on with the test methods and stuff. So this standard basically outlines the procedures and the environmental and EMC test, I would say, required for airborne. DO-160 was first published in 1980 and is currently on revision G. Every airborne equipment from small general aviation aircraft and the rotary aircraft to large airliners and the transport planes must go through DO-160 testing, especially if they have to operate in the United States airspace. The DO-160 standard is equivalent to the European version of the standard, which goes by EUROCADE ED-14. The standard is practically identical with EUROCADE ED-14. DO-160 testing involves a wide range of factors. As I mentioned, this would cover both environmental and the EMC aspect. So from the environmental side, humidity, temperature, then if you talk about electrical interfaces, shock resistance, so on and so forth. I have one slide which lists all the sections which are applicable to the EMC, EMI side, and I will elaborate them more when we go there. So in essence, by going through the testing program or certification program under DO-160, you are making sure your device is reliable, your avionics equipment or module, which is going to go on a commercial aircraft, it is reliable and it will operate correctly in an avionics environment. So that's in a nutshell what the role of DO-160 in the avionics industry in USA is today. Before I go further into the test methods and look at in detail how some of those tests are done, what are the role of those tests, and what are we trying to establish by running those tests to ensure the products are compliant. Again, especially for the benefit of the folks who are new to this standard, please explain what the avionics is. Avionics, simply put, any electronics which go in the commercial aircraft, or I should say in an aircraft environment, basically. So it could be engine control, it could be servo motor, so on and so forth, landing gear, etc., etc. But in today's world, where we are looking a lot more electronics like smart devices, video consoles, and others going in our everyday life, so the Wi-Fi services on the commercial aircraft, the head displays, and any other medical equipment which could be used on board a commercial aircraft to provide emergency medical treatment to the passengers would also fall under the definition of the avionics. So all those equipment, they may not be, some of them may not be essential for the safe operation for the aircraft, like for example a Wi-Fi access point or hotspot. However, the concern there would be that the Wi-Fi access point or similar devices shall not create an unsafe condition which will cause, which will put the flight at risk or flight safety at risk. For example, if the Wi-Fi signal which goes at 2.4 gigahertz and or 5 gigahertz, depending upon which technology are we using 802.11 ADGN or 11 AC. So depending upon which technology is being used, those frequencies may potentially interfere with other equipment which are already on board the commercial aircraft, which could potentially lead to interference and hence cause the safety of the flight at risk. Therefore, it's extremely critical that all the avionics equipment, whether they are essential part of the plane and or they are on board just to provide additional services to the passengers, they go through rigorous testing through the standard like DO-160 to ensure not only they continue to operate as intended, at the same time they do not cause any unsafe condition for other critical equipment on board. Okay, again, for the interest of the folks who are new, very briefly want to say a few words about what is RTCA. As the name says, it's a Radio Technical Commission for Aeronautics. This is a body which is a non-profit body. Its role is to act as an advisory body for U.S. government to guide them about the avionics compliance needs to ensure that the standards or guidelines they come up with, they will ensure the safety or the safe operation of any flight-related electronics or commercial aircraft that by themselves. They come up with different versions of DO-160. By the way, they have very many documents or standard, I should say, which go by typically DO and then next 2 or 3 numbers, which will notate the name of the standard. However, DO-160 is the one which is very commonly requested. And the latest rev on DO-160 is Rev G, which came out in December 2010. They are still working on Rev H. However, the word is that it may come anytime. Typically, RTCA Committee 135, which is responsible for DO-160 standard, issues a release approximately about every 5 years. So it's about the time that the Rev H will be coming out fairly soon. That said, there have been a lot of changes in the industry as we go. If I look at the standards, like 15 years ago when I started my career to where the standards stand today, obviously standards are continuously doing a catch-up work or effort to keep up with the advancement in the technology to ensure the particular area they are covering to provide compliance for the applicable products. They meet all the essential aspect of the products and the technologies being used in those areas. Therefore, we see constant changes in the standard. They are adding new requirements. They are deleting some older obsolete requirements. Standards are going higher and higher in the radiated emission and radiated susceptibility frequency ranges. A good example would be that in the old days, typical radiated susceptibility testing requirement would be 1 gig. It got changed to 6 gig. Now, MIL standard 461 like standard asks for typically up to 40 gigahertz, and we are seeing already some requirement related to Department of Defense where folks are asking for radiated susceptibility up to 77 gigahertz. So the way I see is that as people are moving more and more higher in the frequency spectrum, we will see need to do tailor-made requirement unless standard catch up with those technological advancements, and we'll see needs to do tailor-made testing to correctly provide compliance for the products which will go either in a defense environment or in a commercial aircraft environment. A good example would be that a large number of products today are using the radars at 77 gigahertz, whether they are automotive application or pedestrian application or other application. And at the moment, there are not too many. There are few documents out there, but there are not too many standards out there which will cover those frequencies. Coming back to the point, very quickly want to draw a parallel with MIL standard 461 and the DO-160. Obviously, MIL standards cover the electronic products which go on a military platform, whether those platforms are military aircraft, Navy aircraft, or Air Force aircraft, or they have the ground application, or if they go in the ship environment. So MIL standard 461 will cover those, whereas obviously the DO-160 covers the commercial aircraft environment. That said, the section 22, which is basically about the lightning aspect of the commercial aircraft protection, there have been a discussion going on in industry and efforts were underway for several years to incorporate some aspects of DO-160 and make them part of the MIL standard. So the latest revision of MIL standard 461, which is Rep G now today, which is already out and it's an active document that incorporates a portion of the section 22 as the lightning requirement, and that test is listed as a CS117. So lightning is now a requirement for MIL standard 461G as a conducted susceptibility test, and they are the technical name for this test is CS117. Similarly, they migrated or adopted the ESD, which is I believe section 25 of DO-160, and incorporated that into MIL standard 461G as CS118. So there's been there's a trend to, in a way, harmonize the requirement as where they make sense, and this is part of the effort where some of the harmonization we are seeing, because many of the aircraft environments, whether they're commercial or they have the military aspect, there are parallels. They are not obviously exactly the same. They can't be the same. They are parallels. So based on those parallels, there's been some effort to try to harmonize some of those requirements. So this recent addition of these two test methods to MIL standard 461G is an indication of the acknowledgement that the efforts are underway to harmonize some of these requirements. Okay, this slide shows a brief summary of the test requirement, or in other words, the different various sections which cover different requirements. I have only listed the requirements which are applicable to a commercial aircraft or the avionics equipment which would go on a commercial aircraft related to EMC, EMI aspect of the requirement. my main area of expertise is EMC, EMI. So thereby, I did not try to go into the environmental aspect. For example, the section 1 all the way up to 14 covers various different aspects of the environmental testing. Similarly, section 24, I believe, covers the icing, and the section 26 also covers another different aspect of the environmental testing. So we'll go through some of these more critical test methods. For example, magnetic immunity, there have been some changes, which is covered by section 15. We will look at section 16, power input. We'll talk about why EMC labs would cover, or why DO-160 will address the power input requirement rather than using a different power quality standard. And there are a lot of them out there, like MIL-STD 1275 and similar. We'll look at some other test methods. As I mentioned earlier, we will be talking a little bit more about radio frequency susceptibility in the context of how the testing is done, and look at the comparison with the radiated susceptibility being done in an absorber line chamber versus in a reverberation chamber or mode stir chamber. Towards the end, we'll look at the lightning testing, and then we'll see if we have time, we can talk about some other test methods, or depending upon how the progress is, we'll try to conclude the presentation. Section 15. Okay. The whole intent of the section 15 in a nutshell is to see that if an electronic equipment or avionics equipment is being placed on a commercial aircraft, that the magnetic field it will generate, which all electronic devices will use some level of magnetic field, simply because of the Faraday's law. Electromotive force is equal to the rate of change of flux linkage, basic fundamental principle of any electronic or digital device. So whenever there is a rate of change of flux, or basically there are clocks, there are current flowing, and especially when there is an alternating current flowing or time variant current flowing, the concern, it's all about the physics. It's the nature of how these devices are designed. You cannot walk away from there. So there will be a magnetic field generated, and the intent of this test method is to ensure that the magnetic field generated would not impact other instrumentation on board a commercial aircraft, where the magnetic field generated by a new device does not cause deflection on other indicators or does not negatively impact the performance of other devices. So this test method is defined, a fairly simple test. The way we have defined is they say when you're testing your device, align it in a way that it's align it such that you are moving your magnetic compass or Gauss meter like device, which you will use to measure the magnetic field, along east-west line in a fashion that you could detect a 1 degree deflection on the magnetic compass. So one way is to ensure that your magnetic field is very low and it doesn't cause any deflection. Other aspect of the testing is that depending upon what distance from your device a magnetic compass will create or generate 1 degree deflection, that distance will allow the lab and the manufacturer correctly categorize the device to fall under the correct category. There are 5 different categories which goes from Y, Z, A, B, and C, and that information will find its way in the installation manual, and the installation technician will take additional care when they place this device, and they will have the information that how much deflection or how much magnetic content this device may generate. So it becomes a critical information from that angle to determine at what distance the magnetic field from the device and the test could cause a deflection on the needle. If I talk about the changes from Rev F to Rev G, in essence, I mean, I can talk a lot more detail. In essence, what they did is they try to clearly clarify all the ambiguities in the test procedure, basically showing that the test installation and the compass, which is our Gauss meter, to be properly set up for testing and to correctly determine the distance. So in other words, they provided a lot more clarity on how to set up the EUT, how to align the Gauss meter or the compass, magnetic compass from the EUT, and how to correctly factor in the Earth's magnetic field and everything, so that when we are making a declaration as a laboratory that a certain distance would generate 1 degree deflection, then that correctly relates to the actual field coming from the device. So just to give you an idea, the distances which are determined during the testing could be as low as 30 centimeter to all the way up to 300 centimeter. So that will give you a general idea what sort of reading one would expect about the separation between the device and the test to the Gauss meter when you're performing the magnetic effect testing. I kind of pretty much already covered this slide, so I'm going to jump straight into section 16. Section 16 is performed essentially to determine the EUT, that EUT can operate as required during all different conditions of AC and DC power variations. It's basically a power input test where we are basically essentially testing the power quality, for a lack of better word. In this section, there are quite a few tests which will verify that the EUT does not or will not negatively influence the aircraft power system and will not cause any harmful degradation of the performance of installed equipment. Basically, if I draw a parallel with conducted emission testing, which is required by many of the IT-like standards, for example, say EN 55022 or the newer version of EN 55032, what they do there is that they are looking at conducted emission. That's one simple aspect. Then there are other standards like 61000 3-2 and 3-3, 3-11, 3-12, so on and so forth. And then there are other tests like 61000 3-11, and all these tests collectively basically making a determination that the devices are not pushing harmful interferences or not negatively impacting the quality of the power system installed in somebody's home. Thereby, they will not impact the performance of other devices which are hooked to the power system. So exactly same analogy on the aircraft, where it becomes more critical because everything is in relatively much smaller environment. So it's critical to ensure that when a new device is being introduced and connected to the power bus, that it does not cause any harmful degradation, does not create any harmful frequencies, which will impact the performance of other devices which may already be working correctly. However, they might be a little bit on the margin, and when more interference signals come from the device and the test, that may push the device off the edge and may cause an unsafe condition, which could lead to unsafe condition of the or in other words, put the safety of the flight at risk. So that is, in a nutshell, the whole intent of performing testing for section 16 for the power input. Often a question comes, why not to use a standard like MIL-STD 1275 or other military or avionics standard which covered the power quality? Why to bundle it with DO-160? And when you talk to the experts, a very general explanation provided, which to a large extent makes a lot of sense, is that since all the instrumentation which is used to do the power quality testing are the instrumentation which one would find in an EMC EMI lab, Therefore, it would make a lot of logistical sense to bundle all the power quality related tests into the one standard like DO-160 from avionics perspective. So that's one rationale given out when people ask the question why DO-160 covered this aspect of the testing. Okay, if I talk about the test categories, there are 4. They go by A, B, D, and Z, and basically they indicate the power, the type of the power used by the equipment, and whether the power source is AC or DC. When we talk about the AC, often, especially with the Rev G, they would add 2-letter designator within the parentheses to indicate whether the power source was a constant frequency for CF, narrow frequency, narrow variable frequency, or wide variable frequency. So these are additional clarities which are provided with Rev G, and that basically help clarify what was the power source used during the actual testing and what does the UT support. Another change with Rev G is that the abnormal surge test is specified for each individual phase of a 3-phase power. So there was some level of ambiguity there. Now they have clearly specified that the surge would have to be done for each one of those individual phases on 3-phase power system, whether they are 400 hertz or 115 hertz, 115 volt, 60 hertz system. You will have to do the abnormal surge testing there. Next section I want to jump into is the voltage spike. So the voltage spike-like testing is done. Voltage spike-like testing is done to determine whether it can operate as required during and after the spike happens onto the power line, whether the unit runs on AC or unit runs on the DC. Standard basically does not specify a certain generator or is not married to a certain test method. The standard says basically, hey, as long as you can generate a pulse which has a pulse duration of 10 microseconds and you meet the minimum rise time requirement of less than 2 microseconds, and you can ensure that your generator output impedance is 50 ohm, that is absolutely totally acceptable. So use any generator you like, but you need to characterize your waveform, make sure you have the duration of 10 microseconds, your rise time is less than 2 microseconds, and your source impedance is 50 ohm. Per Rev G, minimum of 50 voltage spikes are applied, and which are generally a 1 minute. There's a 1 minute separation. So after the application of 50 voltage spikes, if the device continues to operate as intended, we'll consider it as compliant. This test method is very, very similar to MIL standard 461F. Just a note that CS106 was not present in MIL standard, I would say 461, 462D. It was not there for Rev E, and they added CS106 in the MIL standard just to give you guys a quick comparison with Rev F. However, when the Rev G came out, the standard writers decided to take CS106 out of the MIL standard, so it's no longer part of the Rev G of the MIL standard today. Okay. The next section I want to jump into is the audio frequency conducted susceptibility, and this is in reference to the power input ports only. So the folks, again, some of you who are familiar with the CS101 out of MIL standard 461, regardless of the revision, the test level is practically identical to what you will see in MIL standard 461 CS101. The idea there is to inductively, using audio isolation transformers, couple the audio signals onto the power line and then ensure that the device under test or EUT under test does not exhibit any signs of degradation of performance. So the challenges there are oftentimes we see that the way the power supplies are designed, many newer designs cannot handle an imbalance at the input impedance. For example, a device might be working perfectly fine when connected directly to a power source. However, when conducted a test like Section 18 or CS101, as part of the test method to inject the signal, we will have to put the secondary winding of the RDO isolation transformer in series to your power lines one at a time. So it's a single phase, we will do phase one, line and neutral. If it's DC, we'll do your power line and the return. And if it's a three-phase system, then depending upon if it's a three-phase 4-wire or three-phase 3-wire, we'll be putting the secondary winding of the transformer in series to your power line one phase at a time. So what happens is that the moment, just take an example of a three-phase system, say a three-phase 4-wire system, the moment an engineer will put the secondary winding of the transformer in series, it immediately creates an imbalance into the phase voltages. And obviously it can add, or it will add lag on the lines, on the voltage lines, basically phase lines, I should say, simply because there is now a significant inductance in the form of the secondary winding of the transformer present there. So that often leads to imbalance into the input power, and that many devices do not like that imbalance. So from test lab's perspective, it becomes a huge challenge to ensure that when we are putting the transformer secondary winding in series, that device will still continue to operate as it's in the intended application as normal. So those are some of the challenges the labs normally deal with when they are testing to Section 18 or CS101. There are ways around it. There are different options, different power rating of the transformer available. So that's a situation we deal on case-by-case basis, but this is a very common occurring in the lab environment, a challenge we have to deal with when we are performing the CS101 like testing. The typical frequency range, if I talk about that, is 10 hertz to 150 kilohertz. So the idea is that using a signal source, we will put that through an audio amplifier. An audio amplifier will feed the signal through audio isolation transformer onto the power line, and the test level, what we will try to achieve would be typically 8% of the nominal AC input. So for example, if the power source voltage is 115 volt RMS line to return for a single phase, then we'll be applying 8% of the nominal voltage as the input signal from 10 hertz to 150 kilohertz. So that's how the typical testing is done. Again, as I said, the intent there is to ensure the device continues to operate as intended during and after the application of the signal. The next section which I want to jump into is section 20, which is radio frequency susceptibility. Radio frequency susceptibility, allow me to rephrase myself. It's radio frequency susceptibility. However, oftentimes we take radio frequency susceptibility only for radiated susceptibility. In essence, this is a very general word which will cover conductor susceptibility as well as the radiated susceptibility. In other words, this section covers the signals which are induced onto the power lines and or IO lines, similar to CS114, and this section also covers the radiated aspect of the susceptibility, which will be coming from radiated sources, a walkie-talkie, a radar transmitter, or AM transmitter, so on and so forth. So in very general terms, if we are talking about radiated aspect of the testing, most of the time when we are generating the field, we are doing the test with 3 different modulations. CW, which is basically continuous wave, no modulation, square wave, AM modulation, and in many cases there is a requirement for pulse modulation. So The first step there is that we work with our customers and their buyer and help prepare our test plan. During this phase of discussion, it's determined whether all these modulations are applicable, or certain modulations are not critical compared to the other, or there is a special need of a different modulation requirement. So based on what the application of the product might be, we work with the customer, we work with their buyer, and we finalize the fine detail how these tests will be conducted, which modulation we use, what will be the exact test level, so on and so forth, including how the device will be set up. A typical frequency range is 100 megahertz to 18 gigahertz. And again, if I draw a parallel with MIL standard 461, MIL standard 461, even though in many cases testing is done up to 18 gigahertz, however, there are requirements for certain platforms where testing would have to be done up to 40 gigahertz. And another comparison would be that the MIL standard levels are only up to 200 volts per meter. That's the maximum, all the way up to 40 gigahertz. Whereas for DO-160 section 20, there is a lot of variation on the field strength requirement, and it all depends upon what category your product falls into. The highest one, which is listed in the standard, is 7,500 volts per meter, which is significantly high compared to the requirement of MIL standard 461. Talking about the categories, there are 7 equipment categories for conductive susceptibility. There are 10 equipment categories for radiative susceptibility. Unlike other sections, I would say most of the section, the section 20 has 2-letter category designation. The first letter indicates the category designation for conductive susceptibility, and the second letter would indicate category designation for radiative susceptibility. So collectively together, these 2 letters will indicate both for conductive and radiative susceptibility what will be the applicable level. And as I mentioned earlier, 7,000 volts, approximately 7,000 volts per meter is the highest which is requested by the MIL standard. My apologies, DO-160, and the lowest, which is category F, is 1 volt per meter. That being said, there are many programs out there which would call in MIL standard 464, and some sections of the MIL standard 464 for certain applications, they would require even the field strength even higher than 7,000 volts per meter. So those are not the requests which come every day. However, whenever those requests, we accommodate them accordingly. With our facility in Santa Clara, California, we have the ability to go up to very easily, and in some cases we can go higher depending on frequency range. We can very easily go up to 20,000 volts per meter without any issues, up to 40 gigahertz. So if you guys have any need which is about that range or higher, please do talk to us, and we can come up with a plan to accommodate your need there. If I talk about the updates compared to the previous version of the DO-160, so Rev-G basically did an extra effort to harmonize the requirement with some of the FAA advisories to be more consistent. So that is one of the main changes there. Another aspect of the DO-160 is that, which I mentioned earlier, is that the test level like 7,200 volts per meter or higher, they are extremely difficult. It's doable, absolutely doable. But please don't take me in the wrong way, they're absolutely doable. But the challenges would be there that the amount of the amplified power and the antenna sizes, transmit antenna sizes, and the cabling requirement, cabling power handling requirement would be enormously large, and that becomes in many cases a prohibiting factor. Not only the cost, the size, the sheer size becomes a prohibiting factor to use that test method, the absorbent line method, to do generate 7,000 volts or similar test level. So an alternate approach, which is endorsed by both MIL standard and by DO-160. The main standard there is that IEC 61004-21, which gives you all the guidelines how to calibrate your chamber, whether you want to go more tune mode or you want to go stir mode, whichever approach you want to go. So the standard provides all the specific fine detail. Point here is that with the application of the reverberation chamber, labs can, like we do, generate much higher field with reasonably small amount of power, and we have much larger coverage, meaning reverberation chamber would give you a much larger uniform field within the chamber, and reverberation chamber by definition are very large. Simply if you want to accommodate the lower frequency, so a chamber which would start at 100 megahertz compared to a chamber which will start at 80 megahertz, there will be significant size dimension increase to cover the lower frequency. Higher frequency is less of a challenge. At higher frequencies, close to 40 gigahertz, the material or the conducted material of the panels inside the chamber, that will come in discussion, but the size will be less of the discussion. More of the discussion would be the physical dimension, the size of the cavity resonator in essence. So if I talk about that very briefly, this slide basically shows a typical setup in a reverberation chamber. You guys can see that in this setup, the picture shows there is one horizontal tuner, there are two vertical tuners. So these tuners, in many cases, a chamber could be designed only with two tuners, one horizontal, one vertical, and it all depends upon what level of step size you want to achieve, what resolution you want to achieve, what level of accuracy you want to achieve, and what sort of plane field within the chamber you want to achieve. So all those things collectively together determines your chamber design. In this particular example, the cube in the middle of the picture indicates the plane field. So the way the testing is done during the calibration, it's determined how much forward power for the applicable frequency band has to be pumped into using a transmit antenna. And then using the receive antenna and the field probes, we carefully monitor the field being generated and the tuner position which are determined during the calibration process. The software will go through all those steps, the fine steps, and the step size again depends upon which particular frequency range, which particular application you are going for, and using those tuner positions, using the transmitted power with relatively lot less amplified power, we can generate significantly higher, very significantly higher magnetic field there. Here's a brief example of how the plane fields are generated. Again, if I draw a parallel with the absorber line chamber, in absorber line chamber, we do an intentional effort by putting the absorber all around on the walls, on the floor, on the ceiling, to create an environment which we refer to as an anechoic chamber, meaning we want to minimize the echoes, or in other words, we want to create an environment which would be a free space environment. However, in the reverberation chamber, we want to purposely generate more echoes, meaning we want to get more reflections. So by getting more reflections and by tuning those reflections with the help of the tuners, vertical and horizontal, we want to tune those reflections in a way, and please note, when these reflections come, they will add, they will subtract. And this addition and subtraction is not a scalar addition or subtraction. It's electric field is a vector quantity. It has a magnitude, it has a direction x, y, z. So it will have three components. So when the reflections come from the walls, from the ceiling, from the floor, or from the device and the test itself, they all will add in a vector fashion, and we can tune those addition subtraction in a fashion with the help of the tuner that we can maximize the standing waves in the middle portion, or what we call our quiet zone. I shall not use the quiet zone in our test area to maximize the field being generated with the help of the standing wave, with the help of basically the reflected wave, basically. So that is the technique which is used in a reverberation chamber to generate very, very high fields, and thereby with a small amount of power using the reverb chamber, people generate much higher fields to satisfy the need of a test standard like DO-160. MIL standard also covers that. There are a lot of automotive standards which require which you cannot test if, unless you have a reverberation chamber to meet the high field strength requirements. Having a reverb chamber gives us capability to do cover a lot of different ground. We can do cable testing, we can do material testing, we can do testing like Hero and Hertz like require. There are a lot of automotive requirements which can be covered along with DO-160 using the reverberation chamber. Okay, folks, we are getting close to the end of the presentation, and I will try to quickly wrap this last section I want to talk about, which is section 22, the lightning induced. This section by itself is fairly large and covers a lot of ground about the lightning induced transient. And before I jump into, just to do a quick comparison, there are two lightning tests. One is called indirect lightning and other is called direct lightning. So section 22 covers the indirect lightning, whereas section 23 covers the direct lightning. Again, for the folks who the EMC, EMI word, and the DO-160 like requirement, I want to very briefly explain the main difference between lightning, indirect lightning, and the direct lightning. Let's take an example of a power line. Power line might be hundreds of miles long. For example, I mean, I'm based in California, and some of our power still comes today from British Columbia. And imagine the length of the power lines coming all the way, which is exactly physical power, physical lines running all the way from British Columbia all the way up to in California. So imagine power lines are running hundreds and thousands of miles, and somewhere on the line, a lightning strike happens, and lightning hit the power line. When the lightning hits, it's enormous amount of power. It's enormous amount of power, which basically energy. It's enormous. My apologies there. It's enormous amount of energy which will induce currents, and those currents will flow onto the power line. And when those induced currents will couple to various devices connected on the power line, that will be your indirect lightning. That will be the indirect aspect of the lightning, because lightning did not directly hit the device in the test. Okay. On the other hand, if there is a electronic device is deployed in the field somehow, and the lightning hits it directly, there's a direct lightning strike. Like if the lightning hits a antenna, for example, then that is your direct impact, and in that case, the concerns are different compared to the indirect. In the indirect lightning, the concern would be more so the device obviously shouldn't get damaged, but it should continue to operate. With the direct lightning, the concern would be that the device obviously may get destroyed, but it gets destroyed in a fashion that it does not take that harm to the rest of the power system and spread that damage. So there will be two different aspects of what the expectation by doing those tests to determine what the compliance or pass-fail criteria there is. You can apply the exact same analogy to the avionics environment, where direct lightning would mean lightning hitting directly on the plane, and plane obviously is typically a huge metallic structure. I mean, if I take the example of older planes, newer planes obviously have a lot of composite material and stuff, which we'll talk about shortly. And with the indirect lightning would mean that lightning strike happen, which induced currents into the surface. Those currents got induced into the power lines and other communication buses within the commercial aircraft. And when those induced currents find their way to the communication electronic devices, how would they interact? How would your devices interact? How would they respond to those transients which are in the indirect lightning effect, basically? So those are some of the challenges which this testing will help you determine whether your device is designed and hardened in a way that they can handle that sort of transient which will come from the lightning and indirect lightning. So talking about section 22, I mean, anybody who is an aircraft manufacturer or who is selling or building equipment which will go in an aircraft, commercial aircraft, they will need to this sort of testing. I have listed some of the major aircraft manufacturers from various parts of the world. For example, if you look at USA, you will have Boeing, Cessna, Raytheon, so on and so forth. I mean, talking about Canada, we talk about Bombardier is a very well-known name. From France, it's Airbus, so on and so forth. So there are quite a few well-known names who actively follow the requirement of DO-160. If not directly, their requirement, for example, Airbus would have some of the requirements which will be above and beyond the requirement of DO-160. They are predominantly based on the DO-160 requirement, but some of their waveforms are slightly different. So you will see some derivatives, but predominantly the document would be based on DO-160. I can make the same arguments for other commercial aircraft manufacturers. Okay, another point which I indirectly mentioned when I was explaining the differences between direct lightning and indirect lightning is that the older models of the commercial aircrafts were obviously all metallic structure. There are pros and cons. All metallic structure, yes, plane will be heavier. There will be other challenges from that aspect, manufacturing challenges, so on and so forth. But from the EMC, EMI aspect, from the lightning strikes aspect, having an all metallic structure would give you a perfect Faraday cage-like impact, meaning the external electromagnetic environment will not induce any harmful interferences inside. Even if a lightning strike happens, that will not induce, in ideal words, no electrical currents into the communication and power buses inside. Whenever there will be a seam, there will be a gap, there will be a discontinuity between the different metallic panels, that will be the time where the currents will be induced into the electronics or electrical systems inside. Having that said, the trend in the industry is that for obviously many good reasons, ease of manufacturing, lesser weight of the commercial aircraft, meaning a lot less fuel consumption, so on and so forth. For all those beautiful reasons, many of the commercial aircraft manufacturers are coming with various components of the commercial aircraft being designed with composite materials. The challenge there is that now we're using a composite material which is basically like an insulator in electrical property terms, and therefore it will be practically transparent to RF signal, so RF signal can simply penetrate through. Lightning strike happens, it will see a wide gap if the composite material is used, and therefore the electronics on a commercial aircraft which has large portions made of the composite material would be more susceptible to the lightning-like strikes compared to an older design which is all metallic. That being said, there is an increased need to ensure by deploying the composite material, we are making our commercial aircraft more susceptible for these phenomena, that more rigorous testing is done to standard like a DO-160, especially the lightning portion, section 22, section 23, to ensure that all the electronic equipment in there is hardened and designed in a fashion that even if some currents are induced into the power system, our lines, the design is hardened enough and it has enough protection built into that they can handle those indirect lightning waveforms specifically. So in a nutshell, there are 7 test waveforms. They go by 1, 2, 3, all the way up to 6. As I mentioned earlier, Boeing and Airbus, which are very commonly requested requirements, I'm sure there are a large number of other aircraft manufacturers have their own derivatives or requirements, but these are the 2 I mentioned are most commonly requested requirements. For these folks, they have a slight variation from the waveforms which are specified by DO-160. There are 5 test levels. There are 2 test types. They go by pin injection, cable bundle. Then this slide basically is a nutshell of the requirement, a summary of the requirement from section 22. There are 3 test methods, call them direct, cable induction, ground injection, so on and so forth. And another question which comes all the time, how you read through the test category designation, because all the time when we are talking with our customers and their buyers putting together a test plan, oftentimes the requirements will be spelled out as 5 or 6 different letters depending upon which version of the standard you're using, like B3, G4, L3. So B would mean a table from the standard, which is, in other words, a table is of different various waveforms required, which will fall under category B, and the testing would be required to level 3. So then waveform set G required to level 4 if I go by B3, G4, L3. And L3 would mean the waveform set L and test level 3, so on and so forth. Okay, a very quick presentation of the waveforms. Some waveforms are defined as the current waveform, others are defined as the voltage waveform, and then their characteristics, like for example, waveform 1 is a current waveform, and it's a double exponent, 4.6 microsecond rise time, and 69 microsecond time to have, etc. So I'm not going to read through all of this. I had it there just to provide more information for you guys, so that you have a summary of the requirements for this particular section with you. Okay, I mentioned there are 5 test levels. So test level 1 would mean the most lenient environment, or I would say the least stringent test environment, and whereas test level 4 and 5 are the most severe electromagnetic environment, which will be typically a very mission critical environment. So we at MATLAB have the capability to do all the way up to test level 5. If you guys have a need, we can provide for all the waveforms test level all the way up to test level 5. However, most commonly, I would say about 80% of the time or 85% of the time, the requirement we see are up to the test level 3. Okay, so folks, this is my last slide, and basically, very quickly, just want to kind of summarize what we talked about. We looked at different aspects of the DO-160. We looked at a little bit of the history. We looked at some of the test methods. We talked about some of the changes from changes made with the Rev G. Here and there, we did the comparison and look at the parallels between MIL standard 461G, F and G, and the DO-160G. We look at some of the waveforms for the section 22, so on and so forth. I completely understand it's not possible to cover every single aspect or test method for DO-160 in a single session, and I had to skip some of the things to just in the interest of the time. So if you guys do have any questions, please do email us. We are reaching towards the end of our session. Hardly a few minutes are left, so it may not be possible for me to answer any question while we are in this session today, but I will be extremely happy to respond back to your question via email. So I'm gonna, I want to thank you all again for your time and listening into this webinar. It's much appreciated, and I'm gonna hand it back to Ryan right now. And again, as I said, if you folks have questions, please do send them by email, and we'll respond back with an email. Thank you very much. Have a good day, folks.
So this concludes the presentation portion of the webinar. Tomorrow, an archived copy of this webinar will be available on metlabs.com. Will also be a copy available on YouTube for you to watch again. We will send a follow-up email with a link to that file. And now we can answer some questions that you might have. If you have a question, please type it in the questions area of your control panel. For questions we can easily address now, we will read the question aloud and then give the answer. So quickly, I'm going to turn it back over to Assad, address some quick questions, and it's all you, Assad.
Ryan, we are at the end of the session, so I think it will be better that we respond to the question with the email.
Okay, sure. Not a problem. So any unanswered questions, we'll just reach back out to you and address them individually. And if you have any questions, shoot them in an email to us, however that may be the easiest. So thank you for attending our webinar, and thank you for joining us today. And as I said before, we will post a link in a follow-up email to the presentation so that you have access to it. And that's all. Thank you.